Hello, everyone, and welcome to the second day's Big Science Hour. Today it will be with NASA and the Dragonfly Mission. I'm really excited about this one. I got the opportunity to go to Johns Hopkins laboratory and visit the actual lab, and this mission is pretty much out of this world, pun intended. So, the purpose of the Big Science Hour is to introduce our membership to what's coming down the pipeline. This is one of the best missions coming, in my opinion. It seems to me that wherever there's fluids in the universe, there's likely to be life. And there's only one other body in our solar system with fluids on the surface, and that's Titan. And that's what this is set here to do. I would like to encourage everyone to view our 3 welcome videos. There is the first video, the NSBP video by the E-Board and the Student Council. There is a video by Brookhaven National Lab by Dr. Dune Gibbs. And then there is our other partner, Associated Universities Incorporated, and Dr. Adam Cohen. At this time, I'm going to share my screen, and I'd like to take this moment to recognize our sponsors. So here we go. Start screen share. Let's see if this works like I intended to. All right, there we go. So we have 3 levels of sponsorship: gold, silver, and bronze. We have conference partners. And so they are organized by their contribution, but everyone is definitely highly appreciated. And I'd also like to point out that we have over 35 exhibitors who have supported our conference. We can't throw our conference without the support of our supporters. Thank you very much. And know that what you are doing is not only essential for your own organizations, but for the good and benefit of our nation and our future. So thank you all very much. Now, for the next item, this is a reminder. We are now in the process of running the NSBP elections. We're selecting 3 officers who are going to be running the organization for the next couple of years. So if you have not yet voted, I encourage you to cast your vote online as soon as possible. Now, let me stop sharing my screen for a moment here, if I can figure that out. There we go, that was easy. And I would like to introduce our moderator today. It is Dr. Lene Quick. Now, she is at the Sciences and Exploration Directorate at NASA. Her work focuses on geophysical processes on the ocean worlds in our solar system. And for those of you who are thinking, hey, isn't that just Earth? The answer is no. We got oceans on the surface. We got oceans under rock. We got oceans under ice. We got oceans everywhere. She applies principles of fluid dynamics and heat transfer to model cryovolcanic processes and ocean crystallization on the icy moons of the giant planets and on dwarf planet Ceres. Dr. Lene, I am so envious. I want to do that too. Dr. Quick also studies silicate volcanism on Venus and the moon and utilizes knowledge of the planets and moons in our solar system to characterize Earth-like exoplanets. Dr. Quick is a member of the Dawn, Europa Clipper, and Dragonfly Mission teams, as well as the SSERVI TREX science team. Is that Survey TREX? She is also a member of NASA's Roadmaps to Ocean Worlds team and the OPAC steering committee. And I really like her because even though we were not meeting in person, she would tell me what to do on behalf of NSBP, and I really appreciate that. So without further ado, I'd like to turn this over to the amazing Dr. Lene Quick.
Thank you so much, Hakeem. I did not expect that, but thank you for this wonderful wonderful introduction. We're very excited to be here with the Dragonfly team, and we're going to start out with a wonderful presentation and then follow up with a panel and Q&A. And so to start things off, I am going to hand things over to our wonderful principal investigator, Dr. Elizabeth Zibby Turtle from Johns Hopkins University Applied Physics Lab. Take it away, Zibby.
Thank you so much, Lene. Can you hear me okay?
Yes, we can.
Excellent. Okay, I'm going to share the slides here, and then we'll get started. We're really happy to be here today to talk about the Dragonfly mission. And we've got a panel of team members who are working on different aspects of the mission assembled here. And so I'm going to give a overview of Titan, where we're going, what we're going to do with Dragonfly when we get there, what we want to learn. And then we have a panel, as I said, of several members of the team, including Lene, who can answer questions about different aspects of the mission. Right. So, and of course, I always like to start off by saying that, of course, these missions are the result of the work of a lot of people, and this is from our team meeting actually almost a year ago. And we've all been working remotely, of course, over the last coming up, well, I guess, a year and a half. But it's been great to be able to continue to make progress on Dragonfly and getting back to Titan. So why do we want to go to Titan? We don't know how life came to form here on Earth, and it's hard to study our own prebiotic history because it's kind of overprinted by biology everywhere. So we look to other places in the solar system that can provide information about some of the processes that may have led to the development of life. And in many ways, Titan is most like the early Earth, especially in terms of its chemistry. And so in that respect, it holds important keys to understanding aspects of prebiotic chemistry. So Titan is the largest moon in the Saturnian system of the planet Saturn. So this is Titan here, shown kind of all conglomerated together with its siblings in the Saturnian system. Titan is not only the largest moon in the system, but it stands out because at visible wavelengths, you can't actually see easily down to Titan's surface. And this is because Titan has an atmosphere. It's the only moon in the solar system that has a dense atmosphere, and we'll talk a lot about Titan's atmosphere. And this atmosphere is hazy, and so at visible wavelengths, when you look down from orbit, it's hard to see the surface, and it looks kind of like this gorgeous orange ball. So it's a very unusual place within the Saturnian system, but it's actually a really unusual place within our solar system as well. Titan is between Mercury and Mars in size. And as I mentioned, it's the only satellite that has, or the only moon that has a dense atmosphere. But its atmosphere is actually denser than Earth's. The atmosphere is about 4 times as dense as the Earth's atmosphere here at the surface. So it's actually the second densest atmosphere of all the bodies in the solar system with solid surfaces. So this is just a few facts about Titan. It's the second largest moon in the solar system behind Ganymede at Jupiter. The surface gravity is about 1/7 the surface gravity here on Earth. And the surface temperature out at Saturn is very cold. So it's 94 Kelvin or almost 300 degrees below 0 Fahrenheit. The materials that make up Titan, or Titan's surface and atmosphere, are in some ways very different from those here on Earth. So the bedrock composition is water ice, and the atmospheric composition is actually mostly nitrogen, like our atmosphere, but the next major constituent is methane. And that's where a lot of really interesting things start to happen at Titan. I mentioned the surface density is about, the atmospheric density is about 4 times that at Earth. The pressure is about 1.5 times that here at Earth's surface. And I should say, so this is a kind of true color, what we'd see if we were out there at Saturn looking at Titan. But if you look in the infrared, if you look at slightly longer wavelengths, you can actually see down to the surface of Titan, and I'll show you what the Cassini spacecraft found there. And then, as Hakeem alluded to, Titan is an ocean world, and beneath this water ice crust, there is a deep liquid water ocean in its interior, as we've discovered at many moons in the outer solar system. So the methane in Titan's atmosphere creates this very complex photochemistry. At the top of the atmosphere, the methane is broken down, and the molecules recombine to form very large carbon chain molecules. And these molecules fall out through the atmosphere. They kind of aggregate into larger and larger molecules. And this very carbon rich material ends up covering the surface of Titan. But Titan is an icy moon. And so the water ice crust can melt under certain conditions. And that means you have the opportunity for carbon rich material to mix with liquid water at Titan's surface in its past. It's possible that there's also transport between the surface and the interior ocean, and that may be another way for the carbon-rich material to mix with liquid water. And so it's this opportunity for organics and liquid water to mix for extended periods of time that makes Titan such an important destination in terms of understanding the chemical processes that occur before biology develops. So this is the Cassini spacecraft here on the left. It was a very large spacecraft with a dozen instruments. It spent 13 years at Saturn studying all of the aspects of the Saturnian system, including Titan. And it carried with it this curved part of the spacecraft here is actually the heat shield for the Huygens probe that was built by the European Space Agency. And this was designed to descend down through Titan's atmosphere to make measurements of Titan's atmosphere and land on its surface. So Cassini mapped out the surface of Titan. We hadn't actually seen the surface of Titan at this level of detail until Cassini got there in 2004. So our knowledge of Titan as a system is all still very new. So this is a map of Titan in infrared wavelengths. So it's a false color view, but you can see that there are different colors on the surface, which means that there are different types of material, different compositions of material on the surface. And one of the big questions that remains after the Cassini mission is what specifically these materials are. So I'll talk a little bit about the features that we see on the surface of Titan. So there are these dark areas that show up kind of brown here in this enhanced color view. And it turns out that these areas are actually filled with very large sand dunes. So this is, I should say, this is a synthetic aperture radar image. So the features that you see here that are bright are rough at the wavelength of the radar, which is about 2.2 centimeters. And the features that are dark are smooth at that wavelength. And so these bright areas are kind of rugged highlands, and these dark areas, these dark features are these longitudinal dunes that we see almost all the way around the equator on Titan. So the sand is about sand size, like the sand we have here on Earth, but the composition again is very different under Titan conditions. And so Titan's dunes are actually made of organic sand. So that's another fascinating thing that we're interested to study. Titan has a few impact craters, like Earth. It doesn't have a lot, and that's because there are a lot of active processes modifying the surface, eroding and burying the impact craters. But we do see a few here. There's a very large one here, and this Synlap crater here is over here at the edge of the map. And then we'll talk a lot more about the Celt crater, which is the one here, just about in the center of the map. Titan also has topography. They're mountainous regions. Again, in this radar view, the mountains especially show up as this rugged terrain, and you can see again some of these sand dunes kind of wrapping around them. These are up to 10,000 feet high, so they're not towering mountains like we're used to on silicate planets, but they're good size for an icy satellite. There's also hints of what we call cryovolcanism or cold volcanism, where the lava would be liquid water. So this is one of the areas that Linné studies, is cryovolcanism on icy moons in the solar system. And there are some suggestions like this feature here on Titan, where we have this very deep pit right next to a mountain. And what extends out here looks like a flow field. So it's possible that in Titan's past, there have been these kind of cryovolcanic eruptions on the surface. But in the present day, Titan has hydrology, except that the liquid on Titan's surface and in Titan's atmosphere isn't water, but liquid methane. So again, the methane is playing this key role. And so methane on Titan forms clouds and rains out onto the surface and erodes the surface into channels and even forms lakes and seas. And these very dark features we see especially at the North Pole, are these large seas of liquid methane and ethane. And then there's a field here of lakes. So these very dark or very smooth features are smooth because they're liquid surfaces at the surface of Titan. And this is just some Cassini images of the clouds on Titan as well. So looking down on the North Pole where you have these gorgeous lakes and seas, and you can see in this video, which is hopefully playing over the Wi-Fi and Zoom connections, the clouds moving in this movie that Cassini took. And then the Huygens probe descended down to the surface of Titan. It made a lot of really interesting measurements about the atmosphere, and it sent back this view from the surface of Titan. So on the right here is a picture from our moon, just to give you a sense of the scale of the image here from Titan. So the Huygens probe landed in this gravelly plain, and there are pictures here of, the picture here shows these water ice cobbles a few inches across, and it looks kind of like an outwash plain. So the geography on Titan is surprisingly familiar, even though the materials are very different from the materials that form dunes and and gravel and river cobbles here on Earth. Nonetheless, even under these very different conditions on Titan, we're seeing very familiar terrain. And so we know that Titan has the key ingredients necessary for life as we know it. There's energy in the form of sunlight that drives this very rich photochemistry, and there's the abundant, organic material that results from that photochemistry. And then there's the liquid in the system as well. So there's liquid water, which has been available at sites of impact cratering in the past, where the energy from the impact will melt the water ice crust and create large pools of liquid water that can extend, that can last for long periods of time, and possibly cryovolcanism, as well as down deep in Titan's interior ocean. But there's also a second liquid in the system, and that's the methane. And active methane, which has an active methane cycle, but this liquid methane could potentially support the development of an exotic biological system as well. And on Titan, we can study this chemistry in the context of a very familiar geologic environment with an atmosphere and surface processes that are transporting and mixing materials in ways that would be similar to how materials were transported and mixed on the early Earth. So Titan gives us the opportunity to look for answers to very fundamental questions. What makes a planet, or in this case a moon, habitable? What are the chemical processes that led to the development of life? And even, has life developed elsewhere in our solar system? So we don't think that life as we know it would be terribly happy at 94 Kelvin on Titan's surface. But given the opportunity for chemistry to progress and the amount of time materials have had to mix on Titan's surface, we would be remiss if we didn't look to see if there is evidence of chemistry having taken this leap to biology in Titan's past. But Dragonfly is primarily a chemistry mission to understand the chemical steps that occur before we get to biology. So we know from Cassini where we want to go to look for answers to these questions. We know we have a wide range of surface materials and geologic environments and different processes modifying the materials. And the challenge became, how do we get a capable instrument suite to different places to be able to sample materials, to measure their compositions and make other measurements. But Titan, again, has this wonderful atmosphere. And with the higher atmospheric density and the lower gravity, it's actually physically easier to fly on Titan than it is here on Earth. In fact, a person could put on wings and soar over the surface of Titan. which will have to wait for another future mission. But for now, we're going to send a robotic emissary in the form of Dragonfly, which is an octocopter. It's technically an X8 octocopter. It's got 4 pairs of rotors. And like the rovers on Mars, Dragonfly carries everything with it from place to place on the surface of Titan. We don't have the same infrastructure at Titan that we do at Mars. We don't have satellites that can act as relays, etc. So you just saw the high gain antenna deploy. Dragonfly will do all of its communication to Earth from directly from the surface of Titan. And because we're all used to these, at this point, we're fairly familiar with with drones that we can fly around in the backyard. Dragonfly is a very different scale drone. So I know you don't actually know how tall I am. I'm pretty average height. But this is me with one of the prototype rotors for Dragonfly. So the Dragonfly rotorcraft is about the same size as the Perseverance or Curiosity rovers. So it's a very good size vehicle, which is another kind of demonstration of just physically how much easier it is to fly on Titan, in that we can take this large vehicle from place to place. So Dragonfly is scheduled to launch in 2027 and to get to Titan in the mid-2030s. We actually do direct atmospheric entry. We don't need to go into orbit around Saturn or Titan. We go straight down into the atmosphere. And this is actually a very extended entry process. And people that are familiar with Mars missions hear sometimes about the 7 minutes of terror, because the Mars atmosphere is very thin. It's very quick to get from the top of the atmosphere down to the surface. But for Dragonfly, this is actually going to be about a 2-hour process. And so we're going to be landing here in the equatorial dunes, just south of the Selk impact crater that I pointed out earlier. And so this gives us access in very close proximity to a set of materials that have a variety of different histories. So we have those organic dunes I was talking about. And the interdunes, the areas between the dunes on Titan, often have material with a water ice component. And then we have the crater itself, where organics and liquid water may have mixed in the past. The other benefit of landing in this sand dune area, or the interdunes, is these very wide, flat landing areas. So these are not images from Titan yet. These are images from the Namib Desert, and you can see the dunes here are very good analogs for the types of dunes we have on Titan. So this is an aerial image showing the dunes and these interdunes, and the interdunes themselves make a beautiful flat landing sites. So that's another reason that we like this area. Not only can we get to different materials with which we want to study, but we have these great areas to set down between flights. So the mission plan is to explore for a little over 3 years and to travel possibly up to 180 kilometers, a little over 100 miles, exploring a couple dozen unique sites. It kind of depends on where we land in the landing ellipse, but we'll travel through the dunes and interdunes and then up into the deposits associated with the crater and possibly down into the crater itself. And I should say that this is a very exaggerated vertical scale. So I mentioned that the Titan's topography is pretty muted. The dunes themselves are only 100 meters or so high. And this horizontal distance is 200 kilometers. So it looks really dramatic here, but it's much more subdued, the topography that we'll be exploring. We have actually a strategy, again, because we don't have this infrastructure that we're used to at Mars. Dragonfly actually will do its own scouting. And so from our initial landing site, when we plan to go to another previously scouted landing site, we'll actually fly past that and scout out a new site and then come back to the previously scouted landing site. And so we refer to this as kind of our leapfrog strategy. And this allows Dragonfly to scout things out from the perspective of identifying hazards that we'd want to avoid, but also scientifically to look for landing sites that are of interest. So Titan's day is 16 Earth days long. So again, unlike Mars, no one's going to be living on Titan time. And the nominal plan is to fly once every other Titan day, so about once a month on Earth. So we actually spend most of our time on the surface making science measurements and communicating with Earth. And the science measurements are centered on understanding Titan's chemistry, and then putting that in the context of Titan's atmosphere and its methane cycle. Also the organic materials and the processes that mix and modify and transport organics, not only across the surface, but the opportunity to mix for exchange with the subsurface ocean, and to understand the opportunities for these organics to mix with liquid reservoirs, be they liquid water or liquid methane and ethane. And then we also have the capability to search for chemical biosignatures if chemistry did take the leap to biology at some point in Titan's past. So Dragonfly has 2 rotary percussive drills, one on either side, and these break up the surface material, and we use pneumatic transport to like a vacuum cleaner to bring the material into a mass spectrometer. And this mass spectrometer has a couple different modes to study aspects of the material. So there's a laser desorption mode that's shown in the first example here that gives us information about the composition of different molecules that we sample. And then there's also a gas chromatography mode that allows us to measure aspects of the composition, the structures of the molecules. And one of these possible structures is kind of the handedness of molecules that have the same composition, but a different structure. And this can be an important biosignature if there are imbalances in the preferences of those molecules. So I talked mostly about this already, mostly, and we can, Melissa Traynor can talk about this a lot more, but the mass spectrometer is similar to the SAM mass spectrometer that is on Mars. And so this shows some of the different capability in terms of the molecules we'll be able to detect. We also have a gamma ray neutron spectrometer. This allows us to measure the bulk elemental surface composition beneath the lander. So it gives us kind of context for the very localized sampling that we'll do for the DRAMs, the mass spectrometer measurements. And this allows us to classify the surface material to make decisions about what kind of measurements we want to make with the mass spectrometer. And it may even reveal near surface stratigraphy if we have an organic layer over a water ice substrate. We also have a suite of meteorological and geophysical sensors that will tell us about Titan's atmosphere, Titan temperature, pressure, wind conditions, etc., and also about the surface properties, including seismic sensors that will allow us to characterize the level of seismic activity on an icy ocean world, which will be fascinating to learn. And then we have a suite of cameras that allow us to take images at different scales on the surface as well as in flight, and to build up a view of the terrain around the lander, as well as very high resolution imaging at the sites of the sampling for the mass spectrometer. And we have a set of LEDs that can illuminate the surface at different wavelengths, and this will allow us to distinguish different aspects of the composition. And Jorge Nunez, who's one of the panel members, will be able to talk about this in a little more detail as well. We also have ultraviolet LEDs, because some of the organic materials can fluoresce at when illuminated by UV light. And so it'll be really intriguing to see the surface of Titan illuminated this way at night and see if there are different materials that fluoresce. So in addition to all of the engineering development work that's going on right now, and the science we'll do when we get to Titan, we want to find ways to expand participation in the mission. And so we have a guest investigator program that is targeted at students, and hopefully in the future be broadened to for postdocs. to be able to participate in different aspects of the investigation development and ultimately science activities. So we have our first two cohorts of graduate students who are working on a wide variety of projects. Dragonfly is currently in phase B. This is the second phase of the mission. Launch is at the end of phase D, if that gives a bit of a sense. We're still in the pretty early stages of the preliminary design. And during this technical development phases, we will bring in 3 participants a year with 2-year terms to work on different aspects of Dragonfly and the development of the science investigations and the technical hardware. And then during actual operations, we'll have calls as well for a larger number of participants at that point for, again, 2-year terms to participate during operations. So this is a program we're really excited about in terms of being able to expand participation in planetary exploration, and it funds students for about a third time over these 2-year terms, including travel to team meetings and to present results at conferences and publish results. This is our first cohort. So they've been working with a project for about a year now, and we've just brought on our second cohort. And there's a link at the top here to an abstract by Lene describing the program and some of the work the students are doing. As I said, what we really want to do is find some ways to make it easier for students who don't already have connections to Dragonfly or any planetary missions or NASA missions, and who don't have a planetary science background, to build some networking connections, and in this way to expand training the next generation of mission team members and leaders. Dragonfly has a very long mission timeline. As I alluded to, we don't launch until 2027, which sounds a lot further away than it's going to seem, as we're busy building the spacecraft. And then we're not at Titan until the mid-2030s. So we really have a responsibility to find ways to bridge the generations scientifically as we go through the mission. So I know that was a very rapid overview, but I wanted to make sure there was time to introduce the panel members. I alluded to some areas of the work that some of our panel members are working on, but there's 6 of us here to talk about different parts of the mission. And if everyone is available to speak and introduce themselves, I guess I'll turn it over to Lene to introduce herself, and then we can go through each of the panel members.
Sure. And before I introduce myself, I'll say that we have one panel member that hasn't been promoted to panelist. So if someone could promote Dr. Jorge Nunez, we'd appreciate it. Thank you. And so I'm Dr. Lene Quick from NASA's Goddard Space Flight Center. I am a team member on the Dragonfly mission. I am also the lead for the Student Early Career Investigator program. You can see my educational background here. I am an Aggie Pride. And so I'm originally from Greensboro, North Carolina. I received my bachelor's in physics there and my master's in physics from Catholic University in Washington, D.C., and PhD in Earth and Planetary Sciences from Johns Hopkins University. And I've just put a few things on this slide that that are hobbies or that are important to me. I love to read, most of all, historical novels or historical fiction, but I am a newlywed. I got married and then the pandemic started, so I don't have better hobbies. I'm sorry about that, but it's so good to be here with you all. And I guess, Zibby, I don't know who we have next for introduction, but we'll just go through everyone. All right.
Hey there, my name's Alice Kokor. Sorry, Lene, I didn't mean to interrupt you. I'm a physicist at the Johns Hopkins Applied Physics Laboratory. My background is in astrophysics for my bachelor's and in experimental particle physics for my PhD. I now function as a jack of all trades, which ranges from doing research to being something of a systems engineer. So on Dragonfly, I'm part of the engineering team, and I in particular work on lander mobility, which is how the rotorcraft navigates around Titan. So other things that you might find interesting about me. So here's a picture of me by the Atlas detector at the Large Hadron Collider. That's at CERN in Switzerland, and that's where I did my PhD. Another project I spend a lot of time on is a project called Interstellar Probe, which is a mission concept study to send a spacecraft outside of our solar system to study the heliosphere and the interstellar medium outside of it. You can see here a picture of us doing some LiDAR testing, which is the instrument I'm in charge of for Dragonfly at APL. And then in my spare time, I like to act and sing and dance. So here's a picture of me when I played Belle in Beauty and the Beast, which was a dream role and very exciting. And then I'm also a mom. I got a little puppy. Her name is Chloe, and I got a son whose name is Luke.
All right, thank you, Dr. Kokoros. Who do we have next?
Hi, my name is Adrian Hill. I'm a principal software engineer at Johns Hopkins Applied Physics Lab, and I've been there about 21 years. I'm currently the lander autonomy lead. Our lander is not in Earth contact, is out of Earth contact almost all the time. So we rely on a lot of autonomous operations. So what we call autonomy is our onboard system that it does things that we expect, like it'll orchestrate the entry, descent, and landing sequence when we first enter a Titan atmosphere. It'll also handle things that we don't expect, what we call fault management. We have a lot of redundancy on board, and we rely on it to detect faults, to manage switchovers to redundant components, and so on. And in general, just to keep the lander safe. I've been fortunate. I've been able to work on quite a few missions, NASA missions. I was the autonomy lead on Parker Solar Probe, which is our mission to touch the sun that launched in 2018. Also, same role on Van Allen probes, which studied the radiation belt. Same role in New Horizons, which was our mission to Pluto and the Kuiper Belt and beyond. I was a flight software lead on Messenger, which was our mission to Mercury. And I was also flight software lead for Hubble Space Telescope for the replacement computer that was installed on the Servicing mission back in 1999. In my spare time, probably a little different than most, I'm also a referee in the National Football League. This is my 12th season as an official in the NFL. This is my 3rd year as the crew chief, the referee, the white hat. So I'm the guy you hear into the microphone on Sundays, and I'm very proud of that. I'm the 7th African-American to ever lead an NFL officiating crew. And that between these two jobs, that takes up most of my day, but I am married. I have a wife. We just celebrated our 24th anniversary. And I think that kind of is my story.
All right, thank you, Adrian. We're going to, I assume, Jorge Nunez now.
Yes, hi, hello. My name is Dr. Jorge Nunez, and I am a planetary scientist and astrobiologist at the Johns Hopkins Applied Physics Laboratory. And as Dr. Turtle and Dr. Quick had mentioned, right, that on Dragonfly, I'm involved in the science team, but I'm also the lead for the DragonCam microscopic imager, the LED arrays. And so what's really exciting about those is that it allows us to illuminate the surface, and not only in red, green, and blue colors, just like we see with our eyes, but it allows us to also see in the infrared, so beyond what we could see with our natural eyes, and that will help give us at least the first taste of what we might sample and then ingest and analyze then with the mass spectrometer on the space flight, which Dr. Traynor will tell you more about. So very exciting. So background, obviously, so I had a unique background. I did both mechanical engineer and physics, because wanted more punishment. But But it really provided a really fantastic background that has allowed me to kind of straddle both the worlds of science and engineering. And of course, obviously, I got a PhD, went the science route, and really pursued a PhD in planet and geology, and it's really come in handy, especially with missions, right? Where we're both working both with engineers and scientists, right? And really being able to sort of cross-pollinate and work with both languages, right? And so in terms of activities, right, I've had the privilege to be a mission and team, but also being part of a science team member and as well as the operations team for the Mars 2020 rover mission that's currently exploring Jezero crater on Mars. And so that's picture here sort of the rover. That, just spectacular view that we had. The rover was just being dropped onto the surface of Mars. So that was the first of its kind. And I would love if we had something like that for Dragonfly, to have some kind of picture like that. And of course, right, we just had our first scientific paper come out of the mission, right? And it just made the cover of Science. So it just actually came out today. So it was really exciting. I'm also on team member, deputy systems engineer for the LORI instrument, which is this long-range telescopic camera, just like your typical 8-inch telescope, but it's on a spacecraft. And I'm also on the science team of the New Horizons mission, which is the first mission to fly by Pluto and Charon, so the Pluto system. And just because that wasn't enough, we actually ended up finding and then flying by a Kuiper Belt object even further out into the edge of the solar system. And we flew by this Kuiper Belt object known as Arrokoth. In addition to missions, I also do instrument development. And so I'm the principal investigator of what is called AMIM, the Advanced Multispectral Infrared Microimager. And what it is basically a remote sensing instrument, but that is applied at the microscale. And what it is, just like a geologist's hand lens, it allows you to look at rocks and soils really up close at the microscale, where every pixel tells you compositional information. So you can really map rocks and minerals at the grain scale. And then finally, in terms of hobbies, I love traveling, cooking, and so I really enjoy with my little travel companions over here, especially my wife and then these two little girls who always keep me busy. So yeah, very exciting.
Okay, thank you, Dr. Nunez. Let's go to our wonderful Deputy Principal Investigator, Dr. Melissa Traynor.
Hi, thanks. So I'm Melissa Traynor. I'm a planetary scientist at NASA Goddard Space Flight Center. I have the pleasure of being in the same division as Dr. Lene Quick and working with her. My team role, as mentioned, I'm the Deputy Principal Investigator for the mission, one of two deputies working with Zibby. And I'm also the lead for the mass spectrometer, the Dragonfly mass spectrometer DRAMS, which we're building here at Goddard Space Flight Center. Listing my education, both my bachelor's and then my PhD are in chemistry, and I actually studied Titan and the atmospheric chemistry and all the great organics that are formed in the atmosphere. That's what I started studying when I started my PhD many, many moons ago at the University of Colorado. And I always tell people that my graduate student self would be completely would not probably believe what my current self is getting to do in terms of formulate what it will be like to actually go and be on the surface of Titan and get to take samples and get to measure them. It's something I never could have even dreamed of back then. So I feel very lucky. Some other activities, work activities. I also am really excited to be involved in a newly selected NASA mission Da Vinci, which is to go back to Venus. The bottom left image shows the lonely little probe dropping through an artist rendition of Venus. And this will be the first time that the US sends an in situ mission to Venus since the year I was born. And I won't say what year that was, but it was a while ago. And this probe has some instrumentation on it, including a mass spectrometer, different kind of mass spectrometer than what we have on Dragonfly, but we'll be able to take samples as we fall through the atmosphere, not too dissimilar to what the Huygens probe did at Titan. We'll get to do at Venus, and Venus is the opposite extreme of exploring Titan and thinking through some of the thermal challenges and the other challenges you have. I've also been lucky enough to be a science team member for the Curiosity mission, which has been on the surface of Mars for over 9 years now. And specifically, I work on the sample analysis at Mars instrument. And then finally, for hobbies, I like to go do things such as hiking and camping with my family. This is a photo of us. We went to Yellowstone National Park over the summer. It was really fabulous and beautiful. And I think half of America was there. Everyone was there. It was the most visitors they've ever had, I think, in a single summer, because we're all excited to get out of our house. But we had a great time and really enjoyed exploring the park and getting stuck in a bison traffic jam. So nice to meet everyone.
Thank you, Dr. Traynor. And I said last but not least last time, but I think I really mean it this time, our PI, Dr. Elizabeth Turtle.
Thanks, Lene. Yes, so I'm a planetary scientist at the Johns Hopkins Applied Physics Laboratory, and for Dragonfly, I'm the principal investigator and very interested in the science that we'll be doing at Titan, of course. My background is actually in physics. My undergraduate degree is in physics, and then I went on to study planetary sciences at the University of Arizona. My research was primarily impact craters, so it's kind of neat to be kind of coming back full circle to go explore an impact crater on Titan. Other work activities, I'm also the principal investigator of the Europa imaging system, or the cameras on NASA's Europa mission. So this is a suite of a narrow angle camera and a wide angle camera that will go on the Europa spacecraft. And in fact, we're just building the flight hardware for those cameras now, and hope to send those to be integrated onto the spacecraft in the next several months. And then my primary hobby is rowing. I row with the Baltimore Rowing Club, and I'm hoping to get out tomorrow morning. It'll be a little chilly here on the East Coast, but we're trying to get as many rows in as we can before the winter.
Awesome. Thank you, everyone, for those introductions, and we'll start our Q&A. And get through as many questions and answer as many as we can. What we don't get to answer in this session, we may have a little bit of time in the Dr. Willie Hobbs Moore and Honorable Katherine Johnson breakout rooms to answer more questions, and that will start at 6:45. And so our first question comes from Jessica Harris, and Jessica wants to know what kind of rocket will be used to launch Dragonfly, and where will we launch from?
So NASA selects the launch vehicles for its missions, and that won't happen for a little while yet. We're hoping we'll know soon, but NASA is responsible for selecting the vehicle, and depending on what vehicle is, that will determine where we launch from. So we're still a little too early in the process to know that yet.
Great. Do we have any other questions? I'm waiting for them to pop up. Okay, OJ Tucker at NASA Goddard. Hi, OJ. What do we anticipate will be the biggest challenge for the Dragonfly mission? I'm sure everyone on the panel has a different opinion of that. So I guess we'll start with Zibby and go down the row if we'd like to, go down in alphabetical order after that. Sure.
Let's see. In terms of Titan exploration, I think the biggest challenge is among the big challenges is thermal. That it's a very, very cold place, and so we need every bit of heat that comes off our power source to keep the interior of the lander warm, and that's definitely going to be a challenge. Very briefly, I think another challenge is going to be, deciding what to do when we get there. I think there are going to be a lot of really animated discussions among the science and engineering team as we choose where to go next. It's really exciting to be able to travel from place to place, but it gives us so many options. So I think that'll be a challenge as well, but a fun one.
Alice, what do you think about for the challenge, the biggest challenges, or one of the biggest challenges?
Zibby stole mine with thermal. I feel like that's fresh in my mind because I just had like an hour-long conversation about it this morning, which is it is a big issue. I think to add to that, one of the challenges that I find most difficult is the initial entry, descent, and landing, because we have to do it completely autonomously. So we have to hand the spacecraft all the information it needs and to make all those decisions on its own to pick its first landing site. And I honestly don't think I'm going to breathe during those few hours until we get information back, and I highly doubt any of the other team members will. So.
Okay, Adrian, what are your thoughts on that?
Well, thank you. Well, Alice stole my answer because for me, it is certainly the entry, descent, landing sequence. And Zibby talked about the 7 minutes of terror on Mars, and for me, it's going to be 4 hours of terror. I'm not sure if the more time is a good thing. It's more hours of terror. But I think one of the things with this mission, especially being a flying essentially a flying drone, if this were a normal situation, we would land somewhere and we would take a baby flight, and then we take a longer flight, and we would build up and gain the confidence. But with this mission, we're actually going to be using our full flight system to land. So we essentially, there are no baby steps in this mission to be able to test roto flight. We have to do it right the first time because we're going to transition to powered flight, and we're not going to land with the benefit of thrusters or some type of a bouncy pad. We're actually going to have a controlled flight for that first landing. So I think the challenge of doing that right the first time without the advantage of being able to take those baby steps for me is going to be the biggest challenge.
Awesome. Jorge, do you have something quickly?
I think all the other ones have taken the ones that I would also at the top of my list as well. And I agree with Adrian. I have, because I have the fortunate to, have just 7 minutes of terror, and then we know that, okay, we made it or not. Whereas in this case, it's just going to be hours of agony, to see whether we actually survived. But obviously, you have a lot of confidence in the team and so, but the powered flight is the big one. But of course, obviously I'm interested in cameras, right? And so the spacecraft is going to have to fly autonomously, and of course landing, right, and being able to precisely go where we need to go. And of course, right, we have confidence that things will work, but obviously there's things that are going to get kicked up. What if there's dust that's covered the windows, right? And so so that would be my other concern.
And Melissa?
Yeah, so since one of my big focuses is in trying to measure the surface composition, one of the biggest challenges for us is, we don't know exactly what that composition is. So we have to make sure that our system is ready to sample and measure kind of a wide range of possibilities. We have good constraints, and that's what allows us to do the sort of preparation for both science and engineering that we need to do. But it's also, it's a challenge to make sure you have as much flexibility as you can, and also thermal.
Thanks, everyone. And so we have a good question from Dr. Jasmine Barron. Jasmine says she notices that Dragonfly has skis rather than wheels. Does that mean that it's capable of landing on the liquid methane lakes if it has to? Anyone want to take that?
No, we have skids kind of the same way that helicopters do, but we're not designed to be able to float. And in fact, by the area of Titan that we're going to is near the equator. It's a really long way to get to the lakes and seas. Not that one couldn't dream about a long-term extended mission, but when we get to Titan, it'll actually be northern winter at Titan, and so the northern lakes and seas won't actually be illuminated. So that's another reason that we're going to the lower latitudes. But really quickly, I will mention the Huygens probe that I talked about briefly. When they designed the Huygens probe, they didn't know if it was going to land in a liquid or on a solid, because we didn't have detailed maps of the surface of Titan. So so they had to design it to be able to do either, to land on a surface and make measurements of a solid surface, or to be able to float if it landed in liquid hydrocarbons. So that was a pretty impressive feat of engineering. We have the benefit of the Cassini data and the Huygens data, and so we know much more about the surface that we'll land on.
Awesome. And so can we repeat what the power source is for Dragonfly?
Yeah, sorry, I don't think I went into that in much detail. So Dragonfly is designed to use an MMRTG, or a multi-mission radioisotope thermoelectric generator, which is why we call it an MMRTG. This is the same power source that the Curiosity and Perseverance rovers are using on Mars. There's just it's not that dark at the surface of Titan. It's kind of like a full moon here on Earth. So it's plenty to see by, but it's not enough to generate power. With solar power, we need much larger solar arrays, and we'd be able to carry from place to place. So that's a better heat source from that perspective, and a better power source from that perspective. But it also puts out a lot of what's typically called waste heat. But for Dragonfly, there's no waste heat. It's all good, and so that's part of our thermal solution.
Awesome. Okay, and so it's 6:26. So really quickly, we have, I know that went by so fast. So we have 3 more questions, but 2 of them can be combined, and if we could each just take about 30 to 45 seconds to answer. So what questions are we most excited about finding answers to, and or what's your favorite aspect about working on Dragonfly? So we'll start with Zibby and then go down the line once more, just rather quickly.
Scientifically, what I'm really excited to see is how everything fits together. I like that we can do the detailed chemical measurements, but put them in the context of the Titan environment, the atmosphere, the geology, even the subsurface. So that's what I'm really excited to see. And what I like best about the mission, although it's super exciting to think about flying around on Titan, what I really love about this mission is the team. And it is just so much, it's just so wonderful to work with this great group of people. So that's my absolute favorite part of the mission.
Thanks, Zibby. Alice?
I'd say I'm really excited to establish precedents for flying on a planetary surface and making those hopping flights. I think that's a pretty cool engineering feat. And one of my favorite aspects of working on the mission is the challenges, because it's by far one of the most challenging things I've ever considered. And that's both really exciting and really motivating.
Right, Adrian.
All right. So as an engineer, I really get excited about finding ways that we can maximize data return, get as much data down as possible, whether it be compression or come up with clever solutions. I've worked on so many missions over the years, and most of the missions I've worked on, we've been able to overperform as far as providing science data. We've been able to provide more than has been planned. So I'm really excited to be able to find any way possible to get as much data down to these people that are in this Brady Bunch screen that I'm looking at, and seeing the smiles on their faces. And I hate to repeat answers, but really the people in this mission that are working here and with our partners are the most talented that I've ever worked with. And that really makes the job special. I just can't say enough about the talent that's working in this mission.
Jorge.
Yeah, no, I wholeheartedly agree with Adrian, and Zibby, saying, it's the people of this mission that is, I think, the most exciting part about this mission is being able to have the privilege to work with these just incredible people, and especially working together on just, this mission that's almost putting science fiction into reality. Right. And especially the inclusiveness of this mission in the leadership and all the way from the top to the bottom is just, really treat to be part of this mission and being involved. And I'm really excited just to see, everybody's faces just you know, having had the experience with New Horizons and seeing the planet, you know, Pluto for the first time, just that wow moment is just going to be, you know, very similar feeling when we get to the surface of Titan and just that wow, you know, from in everybody's faces when we like landed and, you know, just getting our first images back. So I'm really looking forward to that.
All right, Melissa.
So I agree with everything everybody said. So I can reiterate how much I love working on this team, how much I love working with all these people, and also how exciting it is to face so many, you know, first-time challenges. We're solving problems that no one has had to think about before. No matter how many, you know, different mass spectrometers may have been built in this group I work in, you know, these are really unique challenges, and they're so fun and so exciting. So it's like the same thing that makes it hard is the same thing that makes it great. And I just want to say that one of the things I'm most excited to find, because I spent pretty much my whole science career thinking about what kind of organic molecules could be on Titan, could be made there, maybe what could they do, different environments like impact craters. And I'm just really excited to see as many molecules as I can. That's a dorky chemist answer.
That's a good answer. I would say for me, one of the things that has been most exciting for me, and I'll give a shameless plug for it, is the student investigator program that I'm running. It's really a chance to broaden participation on Dragonfly and on planetary mission teams, and we're looking for students just like you all. You don't have to have a planetary science background. You don't have to have a geology background, and that's been most exciting for me. I know how it feels to go in a room and be one of the only or the only minority or African-American scientists. And so I'm excited about broadening participation so that I can see other scientists on the team and other engineers as well who look like me. So honestly, that's what I'm excited about. So again, shameless plug, please you all apply, you're overqualified for it. And so I thought that we had to end at 6:31, but looking at the schedule, we still have a few more minutes for questions and answers. If folks have them, I understand if some of our panelists may need to drop off, I understand that. But for right now, we are going to, I'll go to the next question that we have on the list. Are there any plans for Dragonfly for the Dragonfly instrument, provided that one or more of the rotors are damaged? Could it still fly with fewer than all 8? And I don't know who would be best to take that question, so I'll just leave that open.
I could take it. Yeah, so we are designed in that we can fly if a single rotor fails. So if we lose one rotor, and because of that pairing, which you see where we have those pairs of rotors in the 4 corners, we can continue to fly with 7 rotors. There are other combinations where we could possibly fly with multiple failures, but that is one. And the question said that if a rotor were damaged, if something really catastrophic happened, like the rotor fell off and, you know, pierced the body of the lander, you know, then we, of course, be in a heap of hurt. But we are single fault tolerant against a single rotor failure.
Oh, I'm muted. Thank you so much, Adrian, for that. Do we have any more questions from the audience? Please type them in if so. Have we really exhausted all of the questions that people were thinking about? Any questions not necessarily about Titan, but I'm sorry, not necessarily about the mission itself, but about Titan as an icy world or the processes that go on there? Okay. Not seeing any. I believe that I am able to pass everything on to Nico Cooper. I believe I'm passing everything on to you in a couple of seconds. I just want to thank our panel again for being here. Thank you, Zibby, Alice, Adrian, Jorge, and Melissa. We certainly appreciate you all coming to join the NSBP family, and you're welcome back anytime. And I will pass things over to Nico Cooper. Nico, are you there?
Thank you so much.
Thank you.
All right,
Hey,
there's
thank
Nico.
you.
Thank you, everyone. I want to again, thank everyone at the NASA Dragonfly Mission at Johns Hopkins and our great, of course, Dr. Lene Quick. So I'm going to be closing things out today. To introduce myself, I'm Nico Cooper, a member of NSBP's Student Council. So I want to thank the Simons NSBP scholars, members of a program of which I'm a former scholar and a mentor. I want to thank our opening speaker, Professor Cora Dvorkin, and every single speaker in our poster sessions and breakout rooms. So I want to remind everyone that after this, in the individual sessions, we have the special events, including more information about this, the NASA Dragonfly mission. We also have a session on HBCUs and a discussion about the future of physics. And we also have our special sessions on light sources and the survey by Dr. Cole. So be sure to drop by everything that you can. As well, we still have our exhibit halls open until 8 p.m. Eastern. So if there's any institution or organization that you haven't gotten to the chance to connect with, be sure to put yourselves out there, and we have our poster session open as well until 8 p.m. when that closes. All right, so finally, to close things out, I want to remind everyone that for the eligible members of NSBP, we still have our election going on, so make sure to cast your vote online before tomorrow. Again, that's tomorrow when the polls close. So closing things out, I want to thank everyone again that's been working super hard to make this conference running smoothly, to be a close approximation to our hopeful norm of an in-person conference, when everyone can get the right resources and everyone can be a good resource for everyone else, and making sure that everything's in its right place. And finally, for tomorrow's schedule, I want to call everyone's attention to the fact that our general session, our opening session, is going to be at 11 a.m. Eastern. So make sure that you're back again bright and early, or whatever time it is for you. All right, and that's all for the announcements that that I wanted to give. And again, I want to thank everybody on this lovely Thursday evening or morning or afternoon, whatever time you have. Yeah, thanks again. Thank you, everyone.